Checker 10 takes a look at sounds and our experience of them. So in terms of what sound actually is, sound corresponds to changes in the pressure of the air around us. And if you've ever put your hands on a set of speakers when they're playing music, you've probably felt those vibrations. Vibrations, like what I'm doing right now, if I clap, create vibrations that travel through the air. Those vibrations change the air pressure, and it creates a cyclical change in air pressure where the molecules of air get squished together periods of time or spread apart, squish together, spread apart, squish together, spread apart. And that cyclical compression and rarefication, or squishing together and spreading apart of the air molecules, create sound waves. Here's a short video that'll show you all about sound waves.
A sound wave is created when a vibrating object, like a guitar string or drum skin, displaces air molecules, causing alternating areas of higher and lower than normal air pressure. These alternating higher and lower pressure zones move through the air away from the source. These variations moving through the air are the sound wave. There are technical terms that describe them. The higher pressure areas are called compressions because they consist of air molecules squeezed together, or compressed, at higher than the normal atmospheric pressure in the room. The lower pressure areas are called rarefactions because they consist of air molecules pulled apart, rarefied, for an area of lower than normal air pressure.
Side of the slide, you'll see a picture, and you can kind of see a visualization of the sound waves. And so again, those are repeating cycles of air molecules that are either squished together or spread apart. And so we're getting more reflection and being able to see the areas where they are more squished together. On the bottom left of the picture, we're seeing a jet plane. So sound travels at the speed of sound, and that corresponds to about 770 miles per hour. And so when a plane is approaching that speed, it creates a disturbance in the air around it, and that disturbance is making the moisture in the air fall out of the molecules of water, are falling out of the air, and it's creating like a little cloud around the plane. And so that's just kind of a fun little, piece of trivia. So the sound waves provide really important information for us. One really important piece of information is they tell us about the loudness of the sound. They convey the loudness of the sound through the amplitude or the height of the wave. And we'll talk a little more about what that looks like. First, let's just talk about our experience of loudness. So loudness is often measured in decibels, the decibel scale. And so if you see here, the D in decibel is capitalized. That's in honor of Alexander Graham Bell. So just another little piece of trivia. It's kind of fun. So we use this scale. This scale is a lot friendlier to us because it's closer to our perception of sound. And just to kind of give you an idea that for every 6 decibel increase in, like say, the volume of something, that loudness is approximately doubling. Okay, so every 6 decibels is an approximate doubling of the sound. Now, we use the decibel scale because the actual sound waves get like enormously big as we go from, say, a quiet whisper to loud music or an even louder jet airplane. And so on the chart on the right side, we can see that at the very bottom I circled a whisper. So a whisper would correspond to about 20 decibels. In terms of the physical sound wave, we can measure that, and it'd be roughly 100. In contrast, if we go up our scale here, we can see that 110 decibels might correspond to, say, loud music that you might be playing. Look how much larger the physical stimulus is. It's 10 million, right? So a whisper is close to 100. But loud music is now 10 million. And then a jet airplane, it would be 180 decibels, and in the actual physical sound waves would be closer to 100 million. So rather than using such large numbers, rather than having such a huge scale like that, we use the decibel scale that, again, is kind of more closely related, not to the physical size of the sound wave, but to how we hear these sound waves. And it's also kind of fun to see evidence of how these sound waves travel through the air and create sound. So there's this simple little demonstration that I'm going to play for you. We're going to tap one of these tuning forks. Now the two boxes are not going to touch, but he's going to tap one. And we'll see if the second one is also vibrating. So it's just a simple demonstration of how the sound waves travel through the air and will make sounds by those vibrations. And the tuning fork can even transfer that sound from one tuning fork to another just by receiving those vibrations. So also on this slide, I just want to point out that the up and down, this vertical arrow, is pointing out the amplitude of the little red sound wave here, that it's the height of the wave, or more technically the amplitude, and that determines the loudness. Now another characteristic of the sound wave determines the pitch, and that is the frequency. So frequency is just how many, or the number of cycles per second, and we measure frequency in terms of hertz, Hz. And so if you've ever bought audio equipment or some headphones or something, if you looked at the detailed information, it probably gave a range of hertz that were able to be played through those headphones, for example. And so that's telling you the range of frequencies that can be heard, say, through those headphones or a pair of speakers. On the left, we have a low frequency wave that would create a very low pitched sound. So think of the keys on the left side of the piano, or a very low, deep voice. The picture on the right has a demonstration of higher frequency waves, so they're repeating much more quickly, the waves are skinnier, and in a 1 second period of time, for example, we're getting many more waves coming into our ear, the high frequency wave than with the low frequency wave. And so the high frequency wave would correspond to a high pitched sound, and it would be, for example, the keys on the right side of a piano, or a very high pitched voice, so soprano, versus the low frequency wave maybe being more like a baritone. And here we can see how the frequencies of sound correspond to the different keys along the piano. And so if you look on the piano on the left, the numbers are smaller, so lower frequency, and up here on the right, they're much larger, higher frequencies.